Number 19. Strike anywhere matches contain a layer of KClO3 and a layer of P4S3. The heat produced by the friction of striking the match causes these two compounds to react vigorously, which sets fire to the wooden stem of the match. KCl3 contains the ClO3- ion, and P4S3 is an unusual molecule with the skeletal structure of this. So now we have 4 things to do, letter A through D. So let's just start with letter A. We have to write the Lewis structures for P4S3 and the ClO3- ion. Okay, so let's just get down to it. They did give us the skeletal structure for the P4S3, so I'm just going to write that one over here. So we got P, maybe we'll have a phosphorus that has the triple bound, not the triple bond, but the 3 single bonds, 1, 2, and 3, to the 3 sulfurs, 1, and this should be maybe a little bit down, it doesn't really matter, S, S, and S. These two have binds with the phosphorus, the 2 phosphorus. This has that bond to the other phosphorus. That's probably why I should have made it a little bit longer. And then these 2 bind to the phosphorus. And then we have a crossover with the phosphorus over here. Okay, so now we just have to draw the Lewis structure, which means basically we have the framework. Let's just add the lone pairs. So let's just start with the phosphorus. Remember, the phosphorus ions, right, the P's over here, there's 4 of them. They all have 5 valence electrons. So this phosphorus up top here only had 3, 1, 2, and 3. So it basically has to have 2 more. So this one has 1 lone pair. This phosphorus has the 3 electrons that made the single bond, 1, 2, and 3. So it has to have 2 more. Same thing down here. So 1, 2, and 3. So I just have to add 2 more. This phosphorus, same thing. 1, 2, and 3. So we need 1 lone pair on the phosphorus. Let's now do the sulfurs. There's 3 sulfurs, S, S, and S. And on the periodic table, sulfur is in group 16 or 6A. So it has 6 valence electrons. We're only drawn 2 here. 1, 2. So I need 2 lone pairs to get the total of 6. 1, 2, 3, 4. Same thing here with the sulfur. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that is the Lewis structure for the P4S3. Now let's do the ClO3- ion. We will do that maybe over here. So the ClO3-, remember, the least electronegative element is in the middle. So the chlorine is in the middle, surrounded by the oxygen, because oxygen is more electronegative than the chlorine. So 1, 2, and maybe I will put this a little bit lower. We'll put the last oxygen on the top. Valence electrons, oxygen is in group 16 or 6A, so it's got 6 valence electrons. So 1, 2, 3, 4, 5, 6. We got 1, 2, 3, 4, 5, 6. And we got 1, 2, 3, 4, 5, 6. The chlorine is in group 17 or 7A. It's got 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. And now this -1 ion, right? That -1 means that you gained 1 electron. And generally speaking, you always add it to the more electronegative element. So just pick 1 because you're only allowed to add 1 more. So I'll just put it right here and make this one a pair. Single bond them up. So we got 1, 2, 3. Let's see if we have the octet rule for any of them. This oxygen is good. 2, 4, 6, 8, which means that I can't add any more bonds over here. But this oxygen has 7. 2, 4, 6, 7. It wants the octet, so we're going to double bind because we got a dot for dot. That one's all good. Same issue here. 2, 4, 6, 7. So I'm going to make that last double bond. Now this one has 8. And chlorine has the expanded octet. That's okay. It's got 2, 4, 6, 8, 10, 12 electrons. But Chlorine has access to d orbitals, so we can do that. And now since there was a charge, I have to bracket it and put a -1 charge. And letter A is done. Now on to letter B. We want to describe the geometry about the P atoms, the S atom, and the Cl atom in these species. Okay, so the P atoms are coming from the P4S3, right? So I have to talk about the geometry for the phosphorus, I have to talk about the geometry for the sulfur, and for the chlorine. So maybe we'll do B, right? And we'll say P atoms, the P atom geometry, the S atom geometry, and the Cl atom. Okay, now when they say geometry, they're saying molecular geometry, which means that we have to know all of our molecular geometries by just looking at Lewis structures. Now, since these phosphorus, they're all the same, right? Each phosphorus here has 3 single bonds and 1 lone pair, so it doesn't really matter which one you look at. I'll look at the top one just because I have the most room here. So, phosphorus is now acting as the center element, right? That means that on your chart, phosphorus would be acting as the A element. The A one is in the middle. And these X's are saying how many other elements is the phosphorus bound to? Well, 1 sulfur, 2 sulfur, 3 sulfur. So I have 3 bonds, and the phosphorus has 1 lone pair. So I'm looking for something on my chart over here. And it turns out that that one is right here, right? The 3 bonds and the 1 lone pair, that's trigonal pyramid. Also, you could know it as trigonal pyramidal. So there's an AL at the end. And that's generally the word that's used. So I'll put that down. Trigonal pyramidal is the geometry for the phosphorus. I'm just going to get rid of the A here because we're moving on to the sulfur now. So what's going on with the sulfur? Well, now we're treating these sulfurs as the central element. And they all look the same, so it doesn't matter which one. I guess we'll use the one on the right. So the sulfur would be kind of like the A in the middle. And how many elements is it bound to? Well, 2 phosphorus. So I got a P, or an X, and an X. And then how many lone pairs? Well, they got 2. So now I'm looking for something that looks like this on my chart, right? So I need 2 X's and 2 lone pairs. That comes out to this one, right next door. Bent or angular is the term here. So the S atom would either be bent or angular. Usually bent is the name that you probably will see for this one. But I guess angular works as well. I'm going to erase the A here. So if you just need to write it down, just pause the video. Boop. And now we got to come over here for the chlorine. So now chlorine is going to be the central atom. That's the A. Now here there's double bonds, but nobody cares when you're doing your geometry because all you care about is how many you're bound to. In this case, you have 3 oxygens that are bound, so that's the 3 X's. So I got an X, and an X, and an X. Chlorine has only 1 lone pair, so this is what I'm searching for. I'm searching for 3 X's and 1 lone pair. And that's the same as this. So both phosphorus and chlorine are both classified as trigonal pyramidal, but they kind of look different, but they still have the same geometry. And I'm just going to erase this. And now letter B is done. So we're halfway there. Now we have to assign hybridization to the P atoms, the S atoms, and the Cl atoms in these species. Okay, so now we're going about these down here and what you have to memorize over here. Now hybridizations are just a bunch of S's and P's and D's. These are basically just talking about the orbitals that are overlapping when you make your bonds. So your S and Ps, your hybridization, SP, SP2, SP3, these all correlate with how many letters are in your hybridization. So for example, SP2 has one S and two Ps. P2 means two Ps. So you have a total of 3 letters. If you tackle on one more P, 3 Ps plus 1 S, right? 3 Ps plus 1 S, that's a total of 4 letters. And those letters correspond to the number of things that are around your element. So 2 letters, 2 things. 3 letters, 3 things. But what constitutes as one thing? Well, one single bond is one thing. One double bond, even though you got 2 lines, it's still classified as one thing. One triple bond, even though you got 3 lines, it's still classified as one thing. And one lone pair is one thing. So maybe we'll put letter C down here, right? So we just need to know the hybridization for the P atom, the S atom, and the Cl atom. Keep in mind that all of the P's are the same. So all hybridization for the P atoms would be the same. All the hybridization for the S atoms would be the same because they're all the same. And then you just have one chlorine. So maybe I'll just add the plural here for S atoms. Okay, so let's look at this phosphorus. What's going on with this phosphorus? Well, it's got one single bond, that's one thing. It's got another single bond, that's 2 things. It's got another single bond, that's 3 things. And it's got one lone pair. That's a total of 4 things. So, 4 things, 4 letters, sp3. So maybe I'll say 4 things, 4 LTRS, that's sp3, and that is your answer over here. Let's do the same thing for the sulfur. So this guy. Doesn't matter which one, they're all the same. So what's going on with sulfur? Well, sulfur has one thing. It's got a single bond. It's got another single bond. That's 2 things. It got 3 things and 4 things. 4 things, 4 letters, also sp3. So 4 things, 4 LTRS, sp3. sp3. Last one for the chlorine. What's going on with the chlorine? Well, it's got one thing. It's got a single bond. Here's a double bond. That's 2 things. Here's another double bond. That's a total of 3 things. 1, 2, and 3. And then you have the one lone pair. That's the 4th thing. So 4 things, 4 letters, sp3. So it seems like they're all sp3. And I guess I'll go blue again. That was fun. And now the last thing is we have to determine the oxidation state and the formal charges of the atoms in P4S3 and the KClO3 minus ion. Okay. So let's see. Where am I going to do this? I guess we'll put it over here. D. So we have to do 2 things. We have to do oxidation states. And maybe I'll just bring this down. So oxidation states. And then we have to do formal charges. Okay. So, and actually what I'm going to do is, let's think about this. The oxidation states are going to be kind of a little hard because some of these are going to be different oxidation states. So what I'm going to do is, I guess I'll just pause the video if you need to write these down because I just need to get rid of these like 4 things, 4 letters because I need more room for the hybridization. Where did that go? Magic. Now it's back. And then, okay. So, now there's 2 ways that we're going to be doing the oxidation states here. So we're going to be doing a formula for this one, and then we're just going to be describing what's going on for this one. So let's go with the P4S3. Now there's going to be different oxidation states for the phosphorus because they're bound differently. Now, oxidation state, if we look at this phosphorus, right? Oxidation state is always talking about the charge when you're binding, right? You either gain electrons or you lose electrons. So you always have to look at what's going on between the bonds. And maybe I'll just put this down as ox state. So oxidation state, ox state, tomato, tomato. Now, since these are lone pairs, these electrons are not going anywhere. These are not going to be lost or gained. You always lose or gain electrons in your bonds. So for all of these, we're going to be looking at the bonds. Now, you have to look at what the phosphorus is bound to because you have to determine which one is going to be more electronegative. For example, when I strip this bond away, and maybe I could do it on this side so that I don't lose the whole question, but if I strip this bond away, all this is 2 electrons. And what's going to happen is the phosphorus is either going to lose the electron to the sulfur, or the phosphorus is going to gain the sulfur's electron to the phosphorus, right? If you lose it, that means that's a plus charge. But if you gain sulfurs, that's the negative. And it always goes by the more electronegative element. Now, between phosphorus and sulfur, sulfur is the more electronegative element. So that means that phosphorus's electron is going to go down to sulfur. That's a loss. So we have a loss here. This electron is also going to be lost to sulfur because that's the more electronegative element. So goodbye. This electron is also going to be lost to the sulfur. So that is lost as well. You have 3 losses here. So if you lose 3 electrons, that's the charge of a plus 3. Now let's look at this phosphorus. What's this phosphorus's oxidation state? Remember, we don't care about the ones that aren't bound. You just look at the 3 that are bound. Well, here is bound with the sulfur again. So you're going to lose that electron because that's going to go to the sulfur. But now for these 2, you're bound with phosphorus. That's the same element. So are you going to lose anything? No. But are you going to gain one? No. What's really going on with these is these 2 are like right smack in the middle. Halfway between phosphorus and halfway between the other phosphorus. So no loss, no gain. So I don't count this bond because it's P to P. And I don't count this one because it's P to P. You only lost 1 electron here. So this phosphorus would have a plus 1 oxidation state. Let's keep going. This phosphorus oxidation state, let's see, this bond is P to P, so no loss, no gain. This is P to P, no loss, no gain. We don't care about the lone electrons, but this bond is towards that sulfur. And since sulfur is more electronegative, that's going to go. So that one's also a plus 1. And this, we'll do ox state. P to P, no loss, no gain. P to P, loss, no gain. These are not bound, so no one cares. And you have a bond to sulfur. Since sulfur is more electronegative, that electron's going to be lost. And you have an oxidation state of a plus 1. Now let's do the sulfurs. Now these are going to look all the same. So oxidation state for this one, ox state for this one, and then oxidation state for this guy. Now for each one of them, you're bound with 2 bonds, and they're both bound to phosphorus, right? Bond to phosphorus, bond to phosphorus. This sulfur, bind to phosphorus, bind to phosphorus. This sulfur, bind to phosphorus, bind to phosphorus. And let me just get rid of this. Okay. So now remember, since sulfur is the more electronegative element, it's going to gain the other electron. So you have a gain here and a gain here. You gained 2 electrons, so that's a negative charge. So for this sulfur, you have a negative 2. You gain 2 electrons. This sulfur, you're going to gain and gain. So that's a negative 2. And this also is a -2 because you're going to gain from the 2 phosphorus. Now, your overall charge, since there was no charge here, it should equal 0. But if you add up all the oxidation states, +3, -2, -2, and then you have 3 plus 1s, that equals 0. So we're good to go here. Now let's do the same thing for the chlorine. Okay. We can do the formula, or we can just do the same thing as we did here, right? Between the oxygen, remember, oxygen is always more electronegative than the chlorine. So, when we look at this oxygen, what's this oxidation state? The 2 dots were for the oxygen, and you have 2 electrons here that you're going to pull to the oxygen. So, you have pull 1 and pull 2. So this oxidation state will be a -2. The same thing goes up to here. So this oxidation state, since you have a double bond, oxidation state, it's also going to be a -2 because you had those 2 electrons from the chlorine that are going to be pulled up. So that's a win-win, -2 charge. And this oxygen is also a -2 because remember, we gained 1 when we added that charge. And then there's another electron from chlorine that's going to be gained. So the oxidation state for this oxygen is a -1. -2. So -2 is all around. And then if you just look at the chlorine, right, how many bonds did it lose? And maybe I can just, there we go. Well, the oxidation state here, you lost this electron, that's going to oxygen. You lost that one, you lost that one, you lost that one, and you lost that one. They're all going to their oxygens. So 1, 2, 3, 4, 5, the oxidation state for the chlorine is a +5. And that's all for the oxidation states. Now we have to do the formal charges. So, formal charge is probably better to do with a formula. So, formal charge. This probably is a review, right? Formal charge is always valence electrons. So I'll say val electrons minus number of bonds. So I'll put this little, this used to mean number back in the day. Now it's a hashtag, but that just means number. So number of bonds minus number of dots, aka your electrons. So we'll say number of lone electrons, the dots. Right? So let's start with the phosphorus, right? Now all these phosphorus are going to be the same now because they all have 3 bonds and 1 lone pair. So we'll say FC, formal charge, right? Football club, for anybody overseas, across the pond. Not here in America, though. But I love Liverpool. I hope you do, too. If you do follow, soccer or football, let me know what your favorite team is. Anyway, let's keep going. Formal charge. Valence electrons for phosphorus on the periodic table is 5. So 5 minus, how many bonds do you see? There's 3 bonds for phosphorus. So 5 minus 3 minus 2 lone electrons. I don't count them as a pair. I count 2 dots. So 5 minus 3 minus 2. Formal charge is 0. And for all of these, your formal charge is also going to be 0 because they all have the 3 bonds and the 1 lone pair. So formal charge for your phosphorus is all 0 here. And now the sulfurs, they're all going to be the same as well because for each one of them, you have the 2 bonds and the 4 electrons. So formal charge equals valence electrons on the periodic table, which is 6, minus, you got 2 bonds going on with the sulfur, minus 4 dots. So 6 minus 2 minus 4 is 0. So same for this sulfur. Formal charge equals 0. And for this one also, formal charge equals 0. Now we got to come down over here, right? So maybe I'll just put FC equals. For this oxygen, what is going on? Well, how many bonds do you see, right? First valence electron for oxygen on the periodic table is 6. There's a double bond, that's 2 bonds. For formal charge, you do count the double bond as, 2 things. So 6 minus 2 minus, there's 4 electrons here, 4 dots. So that's a formal charge of 0. Let's do this oxygen. 6 valence electrons minus 2 bonds minus 4 dots. That's a 0 charge. This one, formal charge equals, for this oxygen, 6 valence electrons minus 1 bond minus 6 dots. That's a -1 charge. And then we'll do it for the chlorine. Valence electrons for chlorine is 7 minus 1, 2, 3, 4, 5 bonds minus 2 lone pairs, or 2 dots. 7 minus 5 minus 2 is 0. And finally, we are done with this one. Oh my goodness. I really hope this helped you out. Let me know in the comments. This one was a crazy one, but if you guys got this, you could do Lewis structures, geometry, hybridization, oxidation state, formal charges. You guys got this. So, thank you so much. If you wouldn't mind, please press the subscribe button to help us out and the channel out. We're almost at 30,000 subscribers, and it's all because of you guys. So, thanks so much for that, and I will be talking to you soon. Bye-bye.